Okay, let's begin. So the first question that we'll try today is to find 4 different models of the theory of dense linear orders where any pair is not elementarily equivalent. Dense linear orders, everybody understands? Yeah, between any 2 distinct elements, there is a third element. Okay. So can you give me at least one example of a dense linear order first? Rational numbers, any other example? Real numbers, any other example? Irrational numbers also satisfy the same property. Any other example? See, if you are given a dense linear order, then any interval in that dense linear order is also a dense linear order. So, some examples of intervals: open 0, 1. Okay, so open 0, 1 in R. Okay, then something else. Yes, so this one, then similarly this one, and similarly close 0, 1. Okay, so now look at all 4 of them. Can you tell me if these are elementarily equivalent or not? They are not. Why? One has a least element which can be expressed as a first order sentence, whereas the other one does not have a least element. And you can similarly distinguish between all 4 of them. Okay, so any pair is not elementarily equivalent. Now the question is, can you do it with 5 models instead of 4? Five models. So if I just talk about rational numbers, then where should I put rational numbers? Is it elementarily equivalent to one of them? First one, can you prove that? It is unbounded, and the theory of unbounded dense linear orders is complete. Similarly, the theory of bounded below only dense linear orders is complete, and the theory of bounded on both sides is also complete. So all these 4 theories are complete if they have at least 2 elements. Yeah, I mean, so that is must. I cannot say that closed interval 1, 1 is a dense linear order which is bounded and it is of model of that theory. No. Yeah, because there is nothing to check there. Yeah, so we do not want singletons. We want that there are at least 2 elements. Okay. So similarly, rational numbers are here. They are elementarily equivalent to this, and in fact every single dense linear order which has at least 2 elements, because if it has 2 elements, then how many elements does it have? Infinitely many. Okay, so all infinite dense linear orders, they are elementarily equivalent to one of these 4. Okay, so you cannot repeat the same exercise with 5 elements. Any questions? Okay, so let us go to the next question. Suppose gamma is a complete theory and has a model of size n, cardinality n, where n is some fixed number. Then can you prove that each model of gamma has cardinality n? How do you express that some universe, some set has cardinality n? It has at least n elements and it does not have n plus 1 elements. Okay. So once you know how to express that, then so let sigma bigger equal n denote the sentence which states that, we have done this in the last tutorial, yeah, which states that there are at least n elements. Does anybody remember the sentence itself? There exist W1, W2 up to Wn such that none of them are equal. This is a finite conjunction, so we just write this. Okay. So let sigma n be the sentence and this sentence I am writing in any language, yeah, because I just need equality, I don't need anything else. So because the language of sets, L sets, is contained inside any other language, this sentence is a valid sentence in every language. So let sigma n be the sentence that sigma is bigger equal n and sigma is bigger equal n plus 1 is not true. Okay. Once we have that, then since gamma is complete, what can we say? And there is some model M of gamma such that M satisfies sigma n, yeah. We must have, so this is a model. What did we say last time? That if you have a model of a complete theory, then what is the theory of that model? That is equal to the deductive closure of gamma. So then gamma bar is equal to theory of M, where gamma bar is the set of all those sentences in an appropriate language such that this happens. So all these sentences in gamma bar are true in M, and conversely every sentence true in M is also in gamma bar. So in particular, see, M satisfies sigma n because it has exactly n elements. So therefore, sigma n belongs to gamma bar. Okay, so now gamma has decided that sigma n is true, it's a logical consequence. So simultaneously, gamma has made a choice that negation sigma n is not true. Therefore, for every model, now you understand? Yeah, so i.e. gamma has sigma n as a logical consequence. This is simply the definition of gamma bar. Once we have this, therefore every model, therefore if M dash is a model of gamma, then M dash satisfies sigma n, i.e. cardinality of M dash is n. Okay, it's a very simple exercise. Any questions? Okay, let's do another simple exercise. Yeah, this is a standard application of the compactness theorem. Okay. So, what we are trying to say here, yeah, that if a theory gamma means it's satisfiable if it has models of arbitrarily large finite cardinalities. So, sorry, this one I should make clear, arbitrarily large finite cardinalities, then show that gamma has an infinite model. Now, first of all, tell me what is the meaning of arbitrarily large finite cardinality? For every n in belongs to n, there is a model of that cardinality. No, that's not true. That's not true. Arbitrarily large cardinalities only means that there is a model of cardinality at least n for every n. So, for every n there is a model of cardinality. So, for each n in omega n bigger than 0, there is a model m of cardinality, model of something, yeah, I have to first say model of gamma such that cardinality of m is bigger equal n. This is what the hypothesis means. It doesn't mean that for every cardinality there is a model. Yeah, that's wrong. So, do you remember the statement that we said earlier when we started with predicate logic? Euclid's theorem on infinitude of primes. Yeah, it says that for every natural number, there is a bigger natural number, bigger equal natural number, which is a prime number. Yeah, that is infinitude of primes. So, there are arbitrarily large primes. Similarly, here we are saying there are arbitrarily large cardinalities of models of gamma. Okay. So, that is our hypothesis. Now, we want to show that there is an infinite model and we had to use compactness. Tell me some ideas. If we are given gamma, yeah, and sigma bigger equal n we just wrote down, right. So, let gamma prime be defined as gamma union sigma bigger equal n, where n is bigger equal 1. Okay. So, what will be the cardinality of any model of gamma prime if it is satisfiable? Sigma bigger equal n says that it has at least n elements, but we are putting all sigma bigger equal n's. So, therefore, if gamma prime is satisfiable, then any m prime modeling gamma prime will have cardinality infinity, yeah, at least aleph naught. Okay. So, therefore, what is our claim? Gamma prime is satisfiable, but thanks to compactness we do not actually have to check for satisfiability, we have to check for finite satisfiability. So, we will show that gamma prime is finitely satisfiable. Okay, how do we show something like this? We take any finite subset. So let gamma naught be a finite subset of gamma prime. Then gamma naught contains only finitely many sentences of the form sigma bigger equal n. So let n be the largest natural number such that sigma bigger equal n belongs to gamma naught. Okay. Then what can you say about gamma naught? It is contained inside the set gamma union singleton sigma bigger equal n. Yeah, I put back all the things which were in gamma. Now this is not a finite set, not necessarily a finite set, because we do not know anything about gamma, whether it is finite or not. Okay, but gamma naught is contained inside this. And what will be a model of the right hand side? It will be a model of gamma which has size at least capital N, and that we know. Yes, so by hypothesis, gamma union sigma bigger equal n is satisfiable, and hence so is gamma naught. Now since gamma naught was arbitrary finite subset, is an arbitrary finite subset, gamma prime is finitely satisfiable, and we are done. So usual applications of the compactness theorem which do not involve adding new constant symbols to your language, yeah, then everything just works fine. Yeah, it's a very simple application. This is even simpler than the coloring problem, or yeah, what else did we do? Koenig's lemma. Yeah, this is simpler than that. Yeah, you just need to know that there are arbitrarily large finite models. So actually this is a very, this statement and this statement, yeah. So here, if gamma is complete and has a model of size n, then in fact every single model of gamma is the same up to isomorphism. Yeah, so this is known as absolute categoricity. But a very interesting consequence of the compactness theorem is that if you have a theory which has at least one infinite model, okay, if there is a theory with at least one infinite model or arbitrarily large finite models by this statement that we just proved, then it has an infinite model of any given cardinality. Okay, a very, very strong statement. These statements we'll see next time in the next week. These are called Leeuwenheim-Skolem theorems. Okay, it's a very strong consequence of this. So for example, you know that there is a dense linear order which is rational numbers. Okay. So what is the cardinality of rational numbers? Aleph naught. But now you ask the question, do I know if there is a a dense linear order that is unbounded on both sides and has cardinality 2 to the aleph naught. So, for example, you do not know about real numbers. Yeah, then Leeuwenheim's-Kolem theorem says yes, there is a model of cardinality 2 to the aleph naught. Then you can also ask it for aleph omega, some cardinal number that you do not necessarily understand. But Leeuwenheim's-Kolem guarantees that it does exist. Similarly, you can also get models, if you know existence of models of a large infinite cardinality, then you can guarantee the existence of models of slightly lower infinite cardinalities. Yeah, so all these statements will be made precise later on. Okay, so we have talked a bit about, we have defined the product structure. Yeah, so just to give you a feel of product structures, I have asked a very simple question here. So 2 less than, what is the ordering on 2? What are the elements of 2 first of all? 0 and 1, okay. And 3 is 0 and 1 and 2. The ordering is the usual ordering, and now we are supposed to show that, first of all, find out the universe of this product structure. How many elements will the universe have? 6 elements. And how are they arranged in the form of a Hasse diagram? In what form? Can somebody draw it on their notebooks and show it to me? Raise your paper. Of course, people who are busy with their phones should continue to do so. Yeah? They are just here for attendance. Yes. Very good. Please draw it. This is very simple structure. Yes, if you don't number them, then 0, 2 appears at the bottom.
Oh wait, I have numbered them differently.
You should call them 0, 1 and 0, 1, 2. Yeah, so this will be 0, 0, 0, yes.
And this will be 1,
That will be 1, 0. 0, 1, 1, 1, 1, 2, correct? 0, 2, okay. Now, we still have to understand a bit about what this structure is trying to tell us. What is the language here? L-ord. Okay, so in the product structure, what happens? A1, B1 is less equal A2, B2 if and only if A1 is less equal A2 and B1 is less equal B2. Right? So, this is the definition. A1, B1 is less equal A2, B2 if and only if A1 is less equal A2 and B1 is less equal B2. So, that is precisely what you observe in this. Yeah? So, 2 coordinates, there is a path between pairs if and only if both coordinates are less equal. Yeah? So, a very simple exercise just to make sure you understand the concept. Fine. Okay. Now, next interesting question. So, we are talking about hypernaturals over here. And these are like real hypernaturals. Yeah, I mean, real means, I don't mean real numbers, but U is non-principal. If U is principal, then what will happen? Star n will be a copy of n itself. Yeah, we saw that yesterday. The dictatorship. Principal ultra filter means that the ultra product, which is the average structure, it is simply the original structure, one of the original structures. So star n is a copy of hyperreals, and you have to show it is uncountable. How do you go about something like this? Find an injection from
a bigger set to
from a bigger set. And which bigger set?
R plus.
R plus, and how do you show that?
Like alpha maps to seal of e power alpha in the sequence.
Alpha maps to
Seal of e power alpha in the
seal.
Yeah, like the seal function.
Sealing.
Yeah, sealing
Sealing of
e power alpha in that sequence.
e to the power alpha n. Alpha is coming from where?
R plus.
Alpha is coming from R plus, and this function is
No, like this, like alpha maps to the sequence seal e power alpha.
let me write it down. I am not sure I understand what's going on. So alpha maps to sealing of e to the power alpha
N.
alpha multiplied by n.
Yeah.
This is a function from
No, like that sequence. Like for, yeah, and then the equivalence class of that thing.
wow. Okay, and how will you show something like this?
Well, like they all diverge and they diverge. Like eventually every term will be different.
Eventually every term will be different, okay.
And so they cannot agree on any infinite set, and every term in the ultra factor is.
They do not agree on any infinite set, so therefore everything, okay. So you choose for alpha in R plus. Yeah, that's what your claim is. This sequence. Yeah, I mean sealing is, I think, usually written like this, yeah, with, right. Okay, perhaps, I mean, we'll have to go into some dynamical systems or things.
No,
I mean, proving that the equivalence class is always different.
no, it shouldn't be like, because if you have alpha less than beta, then e power beta n will eventually like it'll always be greater than e power alpha n.
If alpha is less than beta, then e to the power alpha n will be,
Like sealing of e power beta n will always be greater than sealing of e power alpha n for large.
if alpha is less than beta, then sealing of e to the power alpha n is
less than
strictly less than
yeah,
e to the power beta n eventually.
eventually.
Yeah,
That's it.
okay. Okay, I had an alternate solution, and which is much simpler. Yeah. So because we are talking about an ultra filter U on the set of natural numbers, so either evens or odds will be in U. So either evens, either 2n or 2n plus 1, 2n minus 1 perhaps, yeah, 2n minus 1, which is all the things which can be written of, no, 2n plus 1 is better, or written like this, is in U. So if without loss of generality, assume 2n is in U. Then we can play around with, we can always change the entries. Yeah, the equivalence class means that we can always change the entries which are in a small set, which means now 2n is large. So even if you change the odd entry, they will lie in the same equivalence class. Two sequences will lie in the same equivalence class. So I am going to simply claim that, and therefore these sequences, yeah, I mean given a, okay, maybe I should write. So if f and g are functions from natural numbers to twice the natural numbers, which means even natural numbers, then and f prime and g prime are sequences of natural numbers such that f prime restricted to even numbers. Oh wait, I should have said something opposite. I should say 2n to n. Yeah. So f prime restricted to 2n is f, and g prime restricted to 2n is g. Then f prime is u equivalent to g prime if and only if f is equal to g. Right? Because two functions, they are equivalent if and only if they agree.
So how do we know there's no smaller or large set that they agree on?
Smaller or larger set?
You don't have to agree on
You have to show it. No, you have to show it doesn't agree on every large set. Right? And
Is it on every large set or only any one?
I was thinking that these two sets are different. So eventually you take all these functions and therefore it will be
no, you could take an infinite subset of even numbers and then
infinite subset of even
if
numbers.
they agree that there'd still be like
Okay. Okay, I was thinking that just because we can make a choice here. Okay, I cannot think of any other solution right now. So perhaps, have you written this down properly?
I mean that's all. Like after that, it's obvious like, because every element of the
Yeah, I think that would work. Yep, write it down properly. So this idea doesn't work. Fine. Shouldn't you say r bigger equal 1? No, it by Archimedean property this will be large, right? Okay. Okay, so let's try another exercise, that an element of a ring is torsion free. So just real numbers, yeah, we do not want to talk about an arbitrary element because you probably don't know rings. Yeah, so element of real numbers is torsion free. So let me quickly give you the definition. So A in R is torsion free if a to the power n is not equal to 0 for all n in natural numbers. Okay. So no power of it can be equal to 0. Okay, so which elements of real numbers are torsion free? All. Yeah. Okay. Which elements of, let's say, Z mod 3Z are torsion free? Or what about integers, just integers? Which elements are torsion free? All non-zero elements are torsion free. Very good. Then Z mod NZ, where n is arbitrary.
All except n. Co-prime.
yeah.
Co-prime,
All except multiples of n.
multiples of n. No, multiples of n do not exist in Z mod NZ.
The factors of it.
Factors of n. So if I take 6 and then I take 2, yeah, so Z mod 6Z and I take 2, the equivalence class of 2, then its power is 4, then 8 and then 16, and will it ever be all the
Some root of
some root, some number which has same prime factors as n. Yeah, okay, so that one will be,
like subset of its
A-
prime factors.
no, not a subset. As I just told you, yeah, you consider Z mod 6Z, then what will be the square of 2? 4. What will be the cube of 2? 8 is 2. Modulo 6Z, 8 is 2. Then power 4 will be 16. But 16 modulo 6 is 4. So it will just move between 2, 4, 2, 4, 2, 4. Yeah, nothing else can happen.
For each prime factor, at least one element if it exists, then it becomes 0.
Yes, so all prime factors have to be present as factors of that entry, then it can happen. Okay, fine. I mean that was just a brief introduction to torsion elements. Yeah, and another, yeah. So, do you know that circle is also a group? Yeah, circle also has, like you consider circle with respect to multiplication, then it has torsion elements. Circle as in complex plane circle, yeah, unit radius complex numbers. So which of them will give you 0? I mean 0 is 1 there. Yeah, I mean I'm talking about slightly different concept here, but
Rational multiples of 5.
yes, right. Okay. Anyway, let's come back to this. The question is now, can you express this in a single sentence that it is torsion free? Is the concept of torsion free finitely axiomatizable? You are saying no. Do you have a proof? No means you cannot think of a way. But this is similar to the question that we asked in the last tutorial. Yeah, that is the theory of infinite sets finitely axiomatizable. You have to say something about every single natural number. Yeah, so this is not like for all n, yeah, a dot n, yeah, this could be somebody's idea n times. This is not equal to 0. This one is not a valid sentence because it involves a quantifier over something which is not the universe. What will be the universe? Our universe is a ring, so real numbers. So we cannot vary that quantifier over natural numbers, which is an external object. However, we can add infinitely many sentences of this form. Yeah? So this is not necessarily finitely axiomatizable, it is, but nonetheless it is still axiomatizable. Okay? So we can add a sentence I mean perhaps not a sentence, but a formula theta n of x, which is x dot, I mean now we have to write x dot. Yeah, how do we write that? We usually use, I mean our language is that of rings. So it is L ring and we have F, G, C, E. Okay, this is binary, binary, and then maybe there is an H which is unary, then 0 and 0. This one stands for 0, this one stands for 1 plus, plus dot minus 0, 1. Yeah, these are our notations. So we have to write that G of and so on. Finally, you will have G of x, comma x, and dot dot dot, you come out of it, and that is equal to C, and you put a negation. Okay, so this is the formula which expresses that it is not, x is not a torsion element of order n, and then you have to say that x is not a torsion element of any order n. Yeah, so how do you write that? For all w, yeah, if w is not 0, then theta n of w holds. This will say that every non-zero element is torsion free of order n, and then you put one such sentence, yeah, n less than omega. Now this is a set of sentences. So this is our theory of torsion free. N can be arbitrary.
So we should be like omega 1 and omega 2, like W1, W2, sorry, and theta W2, like if the product is occurring n times.
Product is occurring n times, but the product is of W with itself. So why do we need different things?
No, but we don't like that. How many times we are?
How many times? That's expressed in theta n. Theta n is the formula which says that you do this n times, and n is fixed. Yeah, n is not varying.
Okay.
N is fixed, so I am adding one sentence of this type for each n. So I am not just talking about a single sentence, I am talking about an infinite collection of sentences, and this collection does express what I need. Yeah, so this is the theory of torsion free elements, and we are excluding the obvious thing. 0 is always torsion of every order, so why should we bother adding it anyway? Yeah, so every element is torsion free. You can express it in terms of infinitely many sentences, but this is not finitely axiomatizable. Yeah, maybe let us spend some time talking about 8, because perhaps that is the most difficult thing out of this. So perhaps we are talking about show that the interpretation of a relation symbol in an ultra product is well defined. Okay, how did we define this? I am not doing the function symbol part, I am just doing the relation symbol part. How did we define this relation symbol? We said that given h1, h2 up to hm, yeah, in our universe, no, not in the universe, I don't think I need this, just the product structure, and an M-array relation symbol R. What do we say? That the equivalence classes of all these elements, this tuple of equivalence classes of these choice functions lies in the interpretation of the relation symbol in the ultra product if and only if, I mean this is just definition, so if and only if, what can we say? This set of those indices where the ith component structure satisfies, I mean this is same as satisfies, but H1I up to HNI, yeah, this belongs to the interpretation of the same relation symbol in the constituent structure Mi is a large set. Okay, so tell me how to show that this is well defined. What is the meaning of being well defined? If I choose, like this is a tuple of equivalence classes of choice functions. So if H1 is U equivalent to H1 prime, H2 is U equivalent to H2 prime and so on, HM is U equivalent to HM prime, then we need that the set of indices where H1I dot HNI, HMI, so this is M, sorry, HMI, this tuple belongs to the interpretation RMI, belongs to U if and only if a similar set for H1I, H1 dash I up to HM dash I, this belongs to RMI, this is large. So how do we show something like this, that this is large if and only if the other one is large?
Take the intersection of.
Exactly. Both sets contain something common. What is that common thing?
The points where they are.
Yes, so both of them should happen. Yeah, so the set, so enough to show that the set of all indices such that both of them belong, yeah, H1I comma HMI as well as H1 prime I up to HM prime I, they are both in RMI, is in U. Okay? But this particular set contains what? The set of all those indices where H1I is equal to H1 prime I. Correct? Intersection, the set of all indices where H2I is equal to H2 prime I and so on. Finally, the set of all indices where HMI is equal to HM prime I. Whenever for a particular index H1 and H1 prime agree, H2 and H2 prime agree, all of them agree, then obviously this and that will both belong to it simultaneously. And this one we already know by definition because they are U equivalent. So each one of them belongs to U and therefore ultimately the intersection of all of them belongs to U and therefore everything follows by upper bounds, upward close property. Any questions? Similarly, you show it for function symbols and constant symbols. Now, here, please observe something, that our relation symbols are finitary, and that property is being heavily used here. Similarly, our function symbols are also finitary. That is also being used because ultrafilters are only closed under finite intersections and not arbitrary intersections. You understand? Yeah, so that's why compactness theorem, which is a consequence of Bosch's theorem, it holds for finitary logic but not for infinitary logic. Yeah, lots of things go wrong if your logic is infinitary. So let us end it here. A big thank you to all the in-class students as well as online learners. I hope that you enjoyed this journey through set theory and logic with me, and the course has taught you a few new things. Thanks again.